Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
In this question, we're told an object is moving through a liquid. It has a drag force equal to BV, and we are also given an expression for B based on the viscosity of the liquid. We need to find an algebraic expression for Vx as a function of time, and then we are also asked to find how long it will take for horizontal speed to decrease to 50% based on this expression that we find for part A. So let's go ahead and tackle part A. This will take a little bit of calculus, so if this isn't something that you're super comfortable with, then this will definitely be more of a challenging question. Let's start off with the physics though. So the only force that's going to be acting on this object is the drag force. So we know that the drag force is going to be equal to m times a. And the drag force will be in the negative direction relative to the object's motion, right? Because it's the motion that is opposing, or it's a force that's opposing the motion. So we know that the drag force will be equal to negative BV, and so we can create a little formula here that relates V and A, and this is where the calculus is coming in. So what I'm going to do is I'm going to solve this for A. And what we're going to do is we're just going to define a constant C. So C will be equal to B over M. And I'm going to take this equation and I'm going to use the fact that acceleration is equal to the derivative of velocity and sub that in. So now I've got an equation that says the derivative of the velocity is equal to negative CV. And I can rearrange this to take all of the v's over to one side. That's going to give me dv over v will equal negative c dt. And then we want to integrate this formula to get an expression for v in terms of time. So we're going to integrate from the initial state to some other final state. So in this case, we will integrate from 0 to some time t, and we're going to use v0 as our initial velocity. And the derivative of 1 over v is ln v. So we get ln v minus ln v naught is equal to minus t minus c, t minus 0, so just ct. And we can consolidate ln v minus ln v naught with rules for logarithms. And then we can get rid of the ln by taking or raising both sides to, or taking both sides and raising e to them. So e to the power ln v over v naught, e to the power minus ct, and e to the power ln, that cancels out, and we get v over v naught is equal to e negative ct. And v is equal to v naught e negative ct. Now remember, c is b over m, and we can also substitute in for b here based on what we were given in the question. So with all of the constants written in, we get a final formula that looks something like this. So this is our answer to part A here. We've got an expression. Now in part B, we need to calculate how long it's going to take for the velocity to reach 1/2 of the initial velocity. So what I'm going to do is I'm going to take this formula that we just derived and substitute in 1/2 v naught on the left-hand side. And I'm going to go back to using that constant here for a second, just so I don't have to write that all out. So v naught and v naught cancel. And I want to solve for time here, so I'm going to take the logarithm of both sides. So ln 1/2 ln e to the minus ct. And ln and e, again, they cancel each other out. So we've got ln 1/2 that's equal to negative 0.693 approximately, and that's going to equal negative CT. Let's go ahead and cancel the negative, so we'll just make it positive on both sides. And let's calculate what C would be for this particular scenario that we were given. So let's do a little equation on the side here. So C is 6 pi n r over m. And the n we were given was 1 times 10 to the minus 3. The r is 4 centimeters. So 4 centimeters is the diameter, 2 centimeters is the radius, so 0.02 meters all over the mass, which is 0.033. And so when we put that all into the calculator, we get a value for C here of 0.0114. And you don't have to do this separately, but I just think it's a little bit easier. So let's sub that in here. So we've got 0.693 is equal to 0.0114 times t. So t is just 0.693 divided by 0.0114. And so when we put that into the calculator, we can get a value of 61 seconds. So after approximately 61 seconds, the speed will have decreased to approximately 50% of its initial value if the only thing acting on it is this drag force that we have here. So yeah, that's the answer to this question.
Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
So in this question, we're told that an object is moving through a liquid and it experiences a drag force equal to B times V. We're given an expression for B, and we're asked to do a couple of things based on this information. The first thing that we're asked to do is use calculus to prove this identity here. So basically, it's just a new way of writing the acceleration based on the derivative with respect to x instead of time. And so what we'll do is we'll start off by writing the definition of acceleration based on derivatives, right? So we know that the acceleration is defined as the change in velocity over time, or the derivative of velocity with respect to time. Now, if we want to write this in terms of a derivative with respect to x, we can use the chain rule, right? So remember that we can rewrite v as a function of t as v as a function of t, v as a function of x, that's a function of t. So when we apply the chain rule to this, we take the derivative of the outside with respect to t, as well as the derivative of the inside. So what do we get when we do that? So we've got dvx dx and dx dt. This is just the chain rule. dx dt is defined as vx. So there we go. We have just proven that identity there. Okay, so this is part A. And then in part B, we're asked to find an algebraic expression for the final velocity. And it should be a function of the distance traveled, the radius of the particle, and the mass of the particle, as well as V naught and the viscosity coefficient. So what we can do is we can take this equation that we just found and do some manipulation to it in order to create an equation for the final velocity based on all of those other things. So first, what I'd like you to notice is that we have this expression for acceleration, but acceleration is also equal to the net force over mass. What's the net force? The net force here is the drag force, and the drag force is acting in the opposite direction of the motion. So we've got negative BV is the drag force divided by m, that gives the acceleration. So now we've got another expression for acceleration, which we can plug into the formula that we just found. So let's go ahead and do that. So we've got negative bvx over m equals vx dvx dx. And why did I do that? I did that because now I have an expression that is completely in terms of vx. And something very good, convenient happens here. The vx's cancel. And so now we've got negative b over m is equal to dvx dx. And we can easily create an expression for Vx from this. So what I'm going to do is I'm going to take the dx over to the other side. And this is where a little bit more calculus comes in handy. We're going to integrate both sides from the initial state to the final state. So on the velocity side, we'll start at v0, and then we will end at, the final velocity. So here we go. The derivative of dx is just x, so we get x minus 0. So this is just negative bmx. And dvx, the derivative of that is just vx. So we get vf minus v naught. And so we can take the v naught over to the other side, and we get an expression for the final velocity based on the initial velocity and the distance traveled. Now, at this point, we can also substitute in for b because we were given that information. So we've got 6 pi n r over m x plus v naught. So this would be our final expression based on the variables that we were asked to write this in. So that's for part B. And then for part C, we have to do something numerical with this. So we're given a viscosity, and suppose a 1 centimeter diameter, 1 gram marble is shot horizontally into a tank of 20-degree Celsius water at 10 centimeters per second. So we're asked to calculate how far it will travel before it comes to rest. So we're going to use this formula that we just derived. And let's talk about some of our givens here. So the final velocity we're going to assume is 0 because we're trying to calculate how far it's going to move until it comes, before it comes to rest. The initial velocity is 10 centimeters per second. Let's put that in meters, so 0.1 meters per second. And then we've got a radius of 0.5 centimeters because the diameter is 1 centimeter. So that's going to be 5 times 10 to the minus 3 meters. And then the viscosity coefficient is 10 to the minus 3. What else do we have? We've got the mass of the object is 0.001 kilograms, 1 gram. So I think that's all of the givens that were provided, and we just need to throw that all into the formula and solve for x. So what I did is I calculated b over m separately. I just did that as a separate equation, and I plugged in all of those numbers, and I got 0.0942. And so that gives me an equation. If I go back to the VF equation that I just created, that will give me 0 is equal to negative 0.0942 x plus 0.1 meters per second. And so I can bring the 0.1 over to the other side as well as cancel out the negatives from that. And then I divide both sides of the equation by 0.0942, and that will give a final value for x of 1.06 meters. So this is how far that marble will travel before coming to rest.
Homework pressure? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
In this problem, we've got an object with a cross-section A shot horizontally across frictionless ice. It has a certain initial velocity, and we're told that air resistance is not negligible. There's a couple of things we have to do in this problem, the first of which is show that the velocity at time t is given by the expression in the book. So in order to come up with a expression for velocity, a good place to start is actually F net is equal to ma, because a is basically the derivative of velocity with respect to time. So it is rather a good place to start. So let's go ahead and write out F nets for this object. Now, the force that is providing the resistance is drag, right? And this is the only force that's acting on this object right now. We're told that there's no friction between the object and the ice, so drag is the only thing that is acting on this object. So we're going to sub in drag here, -1/4 AV squared. And that's going to be equal to our max, but of course, as we've already pointed out, max is just the derivative of v with respect to t. So this is good. Now we have an equation based on vx and t, as well as some constants. So what I'm going to do is I'm going to pull everything over to one side that has to do with v. So we're going to go dvx over vx squared. And then I'm going to take everything else over to the other side. So I get a over 4m dt. And just to make the calculation a little bit simpler, I'm going to redefine a over 4m as just a constant c, so I don't have to keep writing that over and over again. So now I've got this equation here, and I can integrate both sides in order to find an expression for Vx. So what I'm going to do is I'm going to integrate from the initial state to the final state. And on the left-hand side, this is a pretty easy integral. We just get t. On the right-hand side, we get 1 over v, and we do need to substitute in the boundary conditions here. So this is going to give us 1 over vf minus, oh, sorry, there should be a negative here. So these two negatives actually cancel one another. And so on the right-hand side, we do get 1 over vf minus 1 over v0, and that's all equal to ct. So we want to solve this in order to get vf by itself on one side of the equation. So what I'm going to do is I'm going to put this right-hand side over a common denominator. Oh, before I do that, I will just pull the v naught over to the other side. And then I'm going to put the left-hand side over a common denominator. So let's do v naught. So I'm going to multiply the top and the bottom here by v naught, and then I can put these two together. So I get 1 plus v naught ct over v naught, and that is equal to 1 over vf. And then if I want to just have vf, I'm going to flip this whole equation. So on the opposite side now we'll have v naught over 1 plus v naught ct. And if I sub back in for c, because remember that is a over 4m, that will give us exactly the expression that we needed. Okay, so this is an expression for the final velocity based on the parameters. Okay, so let's go ahead and do part B. In part B, we have to do something numerical. So we've got 1.6 meter wide, 1.4 meter high, 1,500 kilogram car hits a slick patch of ice while going 20 meters per second. If friction is neglected, how long will it take the car speed to drop to 10 meters per second and 5 meters per second? So what are we going to do here? We're just going to plug in some numbers and solve for t. So first of all, we've got the cross-sectional area of the car is 1.6 times 1.4. So the area we're going to use here is 2.24 meters squared. And the mass is 1,500 kilograms. And we're going to use an initial velocity of 20 meters per second. So first we need to calculate how long it's going to take to get to a final speed of 10 meters per second. So I'm going to sub 10 meters per second in. And what I'm going to do just to make this a little bit simpler is instead of writing out V naught A over 4m, let's just find out what that is first. So V naught A over 4m, if we plug all of our numbers in, we get a value of 7.467 times 10 to the minus 3. Okay, so this is our equation. And we do want to get t by itself. So what I'll do is I'll divide both sides by 20. So I get 10 over 20, which is 1/2, or 0.5. And that's all going to be over this stuff on the right-hand side. And then I can cross multiply. So I'm going to get 0.5. And then the 0.5 is going to multiply the 7.467. So that ends up giving 3.73 times 10 to the minus 3 t and just 1 on the right-hand side. So all we did was multiply this by this. And that's what's on the left-hand side now. Then we can take the 0.5 over to the other side. So we get 1 minus 0.5, 0.5. And finally, we can divide by the 3.73 times 10 to the 3 to get t by itself. And that gives a value for t of 134 seconds. So that's how long it takes to drop to 10 meters per second, quite a long time. And then we can do the exact same calculation, but with a final speed of 5 meters per second to finish off this part. So we're working with the exact same equation. We've just used a different final velocity. So this time when we divide by 20 on both sides, we get 0.75. Okay, and then we're going to cross multiply again. So we get 0.75 plus oh, my apologies, not 0.75, 0.25, 1/4. So we get 1.867 times 10 to the minus 3. T is equal to 0 or equal to 1. And when we rearrange for t, we get a final value here of 402 seconds. So a very long time. But in part C, we're asked whether it's reasonable that we are neglecting kinetic friction here. So in order to assess that, what we need to do is assess the relative sizes of the drag force and the friction force. So we know the drag force is going to be 1/4 AV squared. So for 20 meters per second, that's going to give a value for this object of 224 newtons. which is very small for an object at 1,500 kilograms. And then let's calculate an amount for the friction force. So we know that's going to be equal to mu k Fn. I'm assuming that the car has locked out its wheels because it's slipping on ice. So we are using kinetic friction, not rolling friction here. And we'll assume that the normal force is equal to the gravity force. So mu k mg. The coefficient of kinetic friction I'm going to use is 0.15. I just quickly looked up the coefficient of friction between rubber and ice since there wasn't one in the book, and it said about 0.15. So that's what I'm going to use here. The mass is 1,500 and then 9.8. When you plug that into a calculator, you get about 2,200 newtons. So the friction force on a car like this is going to be a lot higher than the drag force, it seems. And so it's not very reasonable to ignore friction because it's going to give a much higher deceleration than just using the drag force. And there you have it.
Homework pressure? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
So we need to draw an interaction diagram of a weightlifter that stands up from a squatting position while holding a heavy barbell across his shoulders. Okay, so just to kind of give us a sketch first of what this looks like. So sketch it first, then do the interaction diagram, then deal with the system, and then deal with the free body diagram. So he is standing on the surface. This is the earth. Here is our very beautifully drawn guy. And he's going to have ridiculously long arms for right now so that he can hold a barbell. Okay. So we know that he is in equilibrium because as he stands up, he's not moving after he stands up. So the net force will be 0. The barbell is having an upward contact force. The gravitational force should be downwards. So our interaction. BB is the barbell. So first the barbell acts on WL is the weightlifter. The weightlifter acts on the surface and the earth. The surface acts on the earth. So in here there is gravity. So our gravity lines are going to be pink. The weightlifter is also affected by gravity, and so is the surface. So we have those gravity interactions. Here, the weightlifter on the surface, this is the normal force. Okay, so here's our interaction diagram. And then it wants us to find the system. The system is just the barbell and the weightlifter. So this is a pushing force. Okay, and then we want the free body diagram. So let's do the free body diagram of the barbells. So here is your x-axis. Here is your y-axis. So you're going to have a force pointing upwards. It's the force of the weightlifter on the barbell. You are going to have a force downwards. That's the force of gravity on the barbell. And then we are going to have a free body diagram for the weightlifter. So again, here's Y, here's X. So we are going to have a normal force. You are going to have force of gravity on the weightlifter. We're also going to have the force of the barbell on the weightlifter. And so you will have this interaction. The force of the weightlifter is going to go with the force of the barbell on the weightlifter. And these are your diagrams.
Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
So we need to draw an interaction diagram, identify the system, and then draw a free body diagram and use dashed lines to connect the members of an action-reaction pair of a soccer ball and a bowling ball having a head-on collision where rolling friction is negligible. So let's get an idea of what this looks like. So first we're just going to do a general sketch, then we're going to do our interaction diagram, identify the system, and then deal with the free body diagram. So our general sketch is you have the soccer ball and you have the bowling ball right next to each other. They're going to be sitting on a surface and the earth is down here. So we can kind of use this to help us with our interaction diagram. So you have the soccer ball. There is a pushing force that is acting on the bowling ball. You have the surface, and the surface is acting on both of those. These are normal forces. So the surface is also acting on the earth. So let's deal with gravity in yellow. So this is going to be a gravitational force. The barbell is going to act on the earth. Sorry, the barbell. The bowling ball, excuse me, is going to act on the earth. So is the soccer ball. So the yellow lines are your gravity. So part B is for the system. The system is just the soccer ball and the bowling ball. So your system is going to be here, not including the surface. Okay, and now our free body diagrams. So let's do the soccer ball on the left, the bowling ball on the right. Give it a coordinate system for both. Okay, so you are going to have the normal force on both of these. So there's going to be a normal force for the soccer ball, a normal force on the bowling ball. When you're dealing with the soccer ball, you are going to have a force that pushes it to the left, and that is the force of the bowling ball on the soccer ball. You're also going to have a force straight down, and that is the force due to gravity. So all of these are on the soccer ball. So you are also going to have the force of the soccer ball on the bowling ball and the gravitational force that is acting on the bowling ball. And then dashed lines to show action reaction. That is going to be force on the bowling ball and force on the soccer ball.
Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Okay, so we need to draw an interaction diagram, identify the system, and then draw a free body diagram for each object in the system. For a mountain climber using a rope to pull a bag of supplies up a 45-degree slope. The rope is not massless. So let's give ourselves a general sketch, and then we'll do an interaction sketch. So this is 45 degrees. Here are that's our bag of supplies. Here is the mountain climber. He's like pulling the supplies up the mountain. Okay, so let's deal with our interaction diagram. So we have the mountain climber. We have the rope. It says it's not massless, so we have to put the rope in there. There's also the supply bag. So this is a pulling force. This is also a pulling force. You have the surface down here. So here's our surface. Here's the earth. The mountain climber is dealing with the surface. The rope is not dealing with the surface, but the supply bag is dealing with the surface. These have normal forces and they have frictional forces. So normal force and frictional force. You also have the earth, which is down here. So we can add in our gravity. So I'm going to do that in yellow. The surface is acting on the earth, or the earth is acting on the surface. The supply bag is acting on the earth. The mountain climber is also acting on the earth. And the rope. So we have gravitational forces, normal forces, and frictional forces. Our system is just the mountain climber, the rope, and the supply bag. So that green box tells us our system. Okay, so now we need to do free body diagrams of the mountain climber, the rope, and the supply bag. So we'll do the mountain climber, the rope, supply bag. So we're at a 45-degree angle. So for all of these, we're going to have y pointing this way and x pointing this way. So our free body diagram for the mountain climber is you have the frictional force, you have the normal force, the force due to gravity is going to pull you straight down, and then you have the tension on the rope. The tension is going to pull out this way. So if you put this on our coordinate system, this is y, x is a little bit further out this way, and this is 45 degrees. Very similar for the rope. Rope, here is y, here is x. The tension pulls a little bit more on this side. The force due to gravity still pulls straight down, and you have, this is negative x, and you have the tension from the mountain climber. And now let's talk about the supply bag. So same thing, let's give it a coordinate system, so y, x, okay, and then the normal force of the supply bag is going to pull it against y. This is a kinetic friction because it's moving. There is a force due to gravity pulling straight down, and then you have the tension on the rope. And then our connections happen, our action-reaction pairs are on the tension. So this tension goes with this tension, and this tension goes with that tension.
हम तक पैसे? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
So we have a battery-powered toy car that is pushing a stuffed rabbit across the floor. We need to draw an interaction diagram, identify the system, and then draw a free body diagram for each object in the system. So let's get an idea first of what this looks like. So here is your car, here is your rabbit, and it is sitting on a surface. So this is the surface, this is the earth. Okay, so we can tell that the toy car is touching the rabbit. So for our interaction diagram, you have the car, you have the rabbit, there is a pushing force between them. There's also friction. We have the surface down here. The surface is where there is friction, so between the car and the surface there's friction. Between the rabbit and the surface there's friction. There's also a normal force between the car and the system and the rabbit and the system. And then if we are talking about the earth, there is gravity between the car and the earth, the surface and the earth, the rabbit and the earth. So this is our interaction diagram. If we want to know what the system is just the car and the rabbit. Okay, so we also need to do free body diagrams. So while we're doing free body diagrams, let's put an X and a Y axis down. And another one. Okay, so this is your x-axis, this is your y-axis, same on this side. So this is going to be for the car and this is going to be for the rabbit. So the car has a normal force pointing up. It has the force due to gravity pointing down. It also has the force the rabbit has on the car, FRC, and it has the frictional force on the car. And if you're talking about the rabbit, very similarly has a normal force, has a force due to gravity. The friction here is kinetic friction, so F sub k, and then to the right is the force the car has on the rabbit. So with dotted lines, these are our action-reaction pairs.
हम तक पैसे? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
We need to draw an interaction diagram, identify the system, and then draw a free body diagram referring to the figure with the pulley in your textbook. So to start us off, let's do the interaction diagram. So This is block A. This is block B. Between them, there is friction. Here is the rope. Between A and the rope, there's tension. Between B and the rope, there's also tension. Here's the surface. Between A and the surface, there is friction. You also have the earth. Between A and the earth, there is gravity. And between B and the earth, there is also gravity. Make our gravity lines in blue. And then we need to identify the system. So the system is just A and B. So that is our system. Now to draw the free body diagrams, it's easier to work with this if we rotate our coordinate systems. So I'm going to rotate it 45 degrees. It's not quite 45 degrees, but it gives us a good idea of what's happening. So this is block B, and this is block A. So in block B, you have the force due to gravity that's going to pull straight down. You have the kinetic friction of A on B. You have the normal force. And you have the tension, A on B. The acceleration is going up. So that makes this our x-axis and this our y-axis. For block A, you also have the normal force. You have the tension tension B on A. You have the kinetic friction B on A. You also have the kinetic friction on just A. You have the normal force pulling down B on A, and you have the force due to gravity on A. So our interaction pieces, the kinetic frictions. This kinetic friction will go with this kinetic friction. The normal force will go with the normal force, and the tensions are an action-reaction pair. So this is your free body diagram and your interaction diagram.